Optical instruments. The human eye is a remarkably effective organ, but its range can be extended in many ways by optical instruments such as eyeglasses, simple magnifying lenses, motion picture projectors, cameras including TV camera, microscopics, and telescopes. Many such devices extend the scope of vision beyond the visible range. Satellite-borne infrared cameras and X-ray microscopics are just two examples. The mirror and thin lenses formulas can be applied only as approximation to most sophisticated optical instruments. The lenses in typical laboratory microscopes are by no means thin. In most optical instruments, the lenses are compound lenses. That is, they are made of several compounds. The interface rarely being exactly spherical. This is a standard zoom lenses. Altogether, we have 14 pieces, 13 sets of lenses, 2 blue lenses of extra low chromatic aberration, 3 red non-spherical lenses, and so on. Near point PN. If we move the object closer than the near point PN, the perceived retinal image becomes fuzzy, average about 25 centimeters. This is a near point PN. If you move stuff in, then it will be fuzzy. Simple magnifying lenses can be used to resolve this problem. If we put a simple magnifying lenses in front of your eyes so that the object is just inside the focus point as shown in the figure. Now, you put this lens, make this one is just inside the focal lens. The image eye produced by the lenses is then far enough to be seen by your eye. This is a PN near point. Okay. The theta is about h over 25 centimeters. This is tangent theta. When theta is very small, it's approximately to theta. This is a theta prime. Okay. The theta prime is equal to h over f. This is the focal length of the lens. Okay. This one is larger than this one. This one is larger than this one. Okay. The size of the perceived image on the retina is determined by the angle theta prime. And we see the angular magnification m theta equal to theta prime over theta. Theta prime is h over f. Theta is h over 25. So this becomes 25 centimeters over f. Compound microscope. We have an object lens, eyepiece lens, and we make this is a magnifier. We will talk later. We make the object is very close to f1. Okay, and also we let the whole tube, S is much larger than FOB, the focal length of the objective lens. So this is exaggerates. Okay, this is very small. So this is actually we call this S, the tube length. Okay, this is very small. Okay, and then the first image just fall near the inside the second lens focus point. Okay, so this is the one is magnified, as we mentioned before. Let's we talk about lateral magnification for the first lens, objective lens. Okay, the M equal to the lens H prime to object lens H. And this one, okay, suppose this is theta. This is theta. And this is theta too. Okay? So this lens equal to this one, tan the theta. This one is S. And this is a upside down. So we have a minus sine S tan the theta. And this one is equal to this one. This is equal to FOB tan the theta. We'll cancel out the candle star. So for the first lens, objective length, the lateral magnification M equal to minus S over FOB. And then we have a second magnifier. Okay, so the total lateral magnification is M theta. M is minus S FOB. And this M theta we mentioned before equal to 25 centimeter over F eyepieces. Here we have a minus, that means this is inverted image. Refracting telescope. A telescope, we're looking for objects far, far away. So when the light come in, they are parallel. So they will make an image on their focal length plane. Okay, and we make this F1, F2 overlap. This is the focal pulse of this one is overlap with the focus this one. Okay, and we look at this. When we look at this far away, this is the angle. This is the angle object. Okay, and after that we have this angle. Okay, and we make F1 overlap with F2. So okay, or almost near exact. And then we know this one. When we look at the stuff, the original angle is theta objective. After this telescope is theta eyepieces. Okay, yes. And the magnification is for theta is theta eyepieces over theta objective. Okay, and this one equal to H prime over this. This is a F eyepieces, and this one theta objective equal to H over this one. Okay, this one is F objective. Okay, so we cancel out the H prime. We get M theta equal to F objective over F eyepieces. And we make this, this one is much smaller than this one, so can amplify. The design factors of astronomical telescope is very complicated, not as simple as I mentioned. Okay, we have to consider the magnification, okay, light gathering power, field of view, resolving power, spherical aberration, chromatic aberration, and so on. So this is a huge engineering project.
When light beams enter a lens parallel to the axis of the lens, the beams are brought to focus at a single point. When the lens is tipped so that its axis is angled to the light beams, they no longer focus at a single point. This is known as off-axis distortion, or coma.
When lenses are ground with their faces spherical, they cannot bring a light beam to a perfect focus. We can see the effect of that on image formation using this object, lens, and screen. We'll first bring the image to the best possible focus using the entire lens. Now we'll block off the outer portions of the lens with this mask. The image appears slightly fuzzy, but we can bring it to a sharp focus by moving the lens slightly away from the object. Now we'll block off the center of the lens instead of the outer half. The image is now very fuzzy, but can be sharpened by moving the lens closer to the object. Notice that this image is not as good as the image obtained with the center of the lens. We'll use this ordinary glass lens to demonstrate chromatic aberration. This plate has a number of small holes drilled in it, which are lit from the back with a strong white light. When a lens is placed in front of the plate to cast an image of the holes onto this screen, the colors have separated in the image of each hole. This separation is called chromatic aberration. Notice that the separation is greater for the holes nearest the edge. If this concave lens, made of a different type of glass, is added to the first lens and the combination refocused, the images are free of chromatic aberration. This animation shows how different colors of light are brought to a focus at different points by a simple lens. Here is the effect of adding a corrective lens made of glass with a different index of refraction.